In the first lecture, we had some generalities of this program of reducing 6D theories down to 4 dimensions and deriving some property. And in the last lecture, we discussed one particular example in more detail, the so-called E-string theory on torus. Okay. In particular, we have derived this model corresponding to a tube with, say, half a unit of flux, which in this SO16 base that we discussed had this, the flux looked like that, and the model was a simple Wezumino model, like this. And we combined these models in different ways, produced theories with different fluxes, closed these tubes together to form a torus, and then obtained a lot of theories with enhanced symmetries. And for some of the properties, to follow from 6 dimensions, some of the enhancement of symmetries and so on, we needed to use some dualities, which and the only dualities that we have encountered were Seiberg dualities till now. So what I will do today, I will have some comments about generalization of this procedure in several directions. Okay? So one direction that I will mention is that it's not just E-string that you can understand in such a way. There are more general scenarios that are prone to exactly same analysis. What you get with E-string is the simplest model, but basically the same thing you can do. So in particular, taking NM5 branes on AD type of singularity, you basically can do the same. You can, the theory in 6 dimensions, a lot of things about it are, is known, for example, anomaly polynomial, the symmetry. The theory in 5 dimensions is also known for all these models, and the theory in 5 dimensions is some quiver theory which has a shape of the affine Dynkin diagram of the corresponding group. It's not very important, but it's very particular theory. And then you can play this game, study the domain walls, and understand what kind of degrees of freedom live on the domain walls, and construct a lot of theories which have enhanced symmetries. So I will not discuss this general story. It's not just reiterating the same thing that we did with E-string, but with a lot of complications added. However, one thing I want to discuss is some new types of dualities that you can discover by studying very particular types of theories. Okay? So something which appears novel, not to reduce to known Seiberg duality. So I want to mention that. And later we will discuss what happens, or what do we know about compactifications, not on tubes, but on more complicated Riemann surfaces, say 3-punctured spheres and higher genus Riemann surfaces. And if I will have time, I will add add more topics.
So the theories with E1 flux can be identified explicitly?
Yes. So I will discuss.
Guesswork?
Well, in the same sense as this is a guesswork. You guess. I will write, at least in the D case, explicitly what the domain wall theories are, and you check there for anomalies. And basically, this procedure of generating 4D theories, if you wish, is and checking their properties that they are consistent with expectation. That's another check of these domain wall theories. Okay, so before starting discussing this generalization, let me mention something. Mention one example of duality, like where the Seiberg duality enters. Okay. So we have discussed that the basic tube that we have is this tube and corresponds to this flux, and then we can concatenate such 2 tubes together with different values of flux and obtain a tube which has flux F1 plus F2. Okay? And we had several examples. Let me do one additional example to what we had before, as it will take us to other cases that I want to discuss. So for example, let us take exactly this tube and add to it a tube which is half-half, and then all the rest are minus halves. Okay? This should give a theory which has flux which is 1, 1, and all the rest are zeros. Okay? This is actually an E7 times U1 flux. Okay? I mentioned it last time, so this is an E7 flux, and this is also an E7 flux. It's just in a different while, like you do some while transformations which are in E8 but not in SO16, and you obtain such a flux. So if this construction is correct, if you do such a procedure, add two such tubes, then you should get a tube which is in some sense equivalent to such a tube. So let us see how it goes. So again, now we split this flux into 2 and 6. So let me write this as 2. Then we have 6, like that. And then we add to it the 2 are the same as the 2 over here. So we add something which looks like 2, like that. 2. And then the 6 are opposite, so let me write it like this, 6, and like that. And following our usual rules of the game, when we gauge this and add certain fields, the combined theory is given by this cute thing. So we have 2, 2, 2, and then we have an SU2 gauging, and this thing, 6, like that. Okay? This will be the theory. If you remember, we had also another construction where we had 6 pluses and 2 minuses. Then we generated the flux which is 6 ones here and 2 zeros. This was an E6 flux. This was one theory. This is in some sense the opposite thing. And this should be equivalent to this theory. Okay? But it looks different. Okay? But what one can do is notice that this gauge theory is again an SU2 with 6 chiral fields, fundamental chiral fields. So which is SU2 with 3 flavors, and we can just use Seiberg duality to analyze its dynamics. And when you do so, you obtain, you just, you need to add the mesons. So there will be a meson like that. Let me write. So there will be mesons that you will need to add like that, and meson that you will need to add like this, and you need to be careful with details. And in the end of the day, the theory that you obtain is 6, 2, 2, and like that, with nothing which is charged under SU2. So everything which is charged under this SU2 gets a mass. Okay? So this now looks very similar to this theory. Okay? Modulo, you miss these fields that should go to SU2. But this is okay, because this flux is an E7 flux. This flux is an E7 flux, but they are not equivalent. Okay? The punctures that we have defined are the same punctures. We use the same punctures, the same types of punctures, but the flux is differently oriented. Okay? But what needs to be true is if you glue this theory together, say, into torus, it doesn't matter how the E7 is oriented inside the E8, you should get the same theory. And using our rules, it's just the same block as this one. It just differs by these fields that you need to add, but the difference is exactly such that when you glue things together, you get exactly the same theory. Okay?
So let me understand. The orientation of this flux with respect to the holonomy at the ends.
Yes,
That's
exactly, yes. So it's like, if you think it's just, as we mentioned, there are different types of punctures, like there are many, many choices of punctures, and the difference between these two theories is just, if you wish, a choice of punctures. You can always like rotate the flux to be exactly the same, but then the punctures are different. But
if
when
you rotated both the flux and the puncture, then it would have had to be the same.
yes, okay,
You rotated only the flux, but not the puncture.
exactly.
When you close the tube, how should I think about it? There is a flux, and now there is a holonomy also, right?
No, the holonomy is something, it's like it's an intermediate. Holonomy is something which defines the punctures. But the theory is defined only by the flux. The holonomy should not affect the punctures. The theory. It only affects the punctures.
But let's say the flux was 0.
Yes.
This
Well,
take a simple case, okay, of the geometry. Maybe these theories would be here in that case.
yes.
But in that case, when you close the torus off, this holonomy is a physical thing, right?
So you can think about you always have holonomies, and holonomies are continuous parameters which will parameterize the conformal manifold of this theory.
So there are parameters.
So it might be that with different choices you will land on different points on this of this conformal manifold. Like the actual couplings will be different, but you will end on the same conformal manifold. Okay. Okay. So this is another example how duality is natural in this framework. You just for the consistent picture, to have a consistent picture, you always, there are some non-trivial facts that need to be correct, and these facts turn out to be typically known facts about Seiberg duality. Okay.
So again, the holonomies become physical with the punctures because of their boundary conditions at the end.
And that's right. Yes. They determine exactly which 5D gauge theory you get, and that's
Not just the boundary condition, it's actually the reduction.
That's right. So the fact that which gauge theory you have, so what holonomies determine is which 5D gauge theory you get, and if you close to closed Riemann surface, this is immaterial. As we will have now an example with different gauge theories. But as Shiraz said, when you put boundary condition, you use a very particular gauge theory description.
Even if I didn't have boundary conditions, if I have, so let's say I put one holonomy, I get 5D, some 5D theory.
That's
I
right.
put another holonomy, I get some 5D theory.
It doesn't matter.
Now you're saying that 5D theory on a circle should give me the same.
Exactly. The same, it should give me the same theory, which is, there is a conformal manifold. Okay, this was one thing that I was thinking to discuss or not to discuss, so I will discuss it a bit later. So holonomies determine the conformal manifold, and it might be with different holonomies, you will end on different points of the conformal manifold, but you will end on the same conformal manifold.
What I agree is that, holonomy, when you say a holonomy, it's not just that you're specifying the strength of the holonomy, you're also specifying the direction.
Exactly, that's fine.
But now, the fact that you can, any given direction you can vary the holonomy,
That's fine.
that would span
The space of coupling, there is a very big.
But the fact that you can actually take a different holonomy with a different commutant and also get an equivalent theory which lives in the same.
That's
conformal
fine. So
manifold, this is difficult.
this is a very good question. Let me discuss it like in half an hour. That will be more natural. I will discuss what is the space of exactly marginal deformations and so on.
We expect some jump.
No, no jump.
What I'm not understanding is, apart from the boundary conditions, what's the difference between the cylinder and the torus?
Just the boundary condition. This is the concept. This is the most important thing. If you wish, we are compactifying on some Riemann surface, and we're taking the size to be small, and we should turn any possible holonomies in the end. Okay, you should think of 4D theory as flux is quantized. Okay, so flux gives us really different theories. But different types of holonomies are continuous parameters, and they should take us to the same conformal manifold, to different points on the same conformal manifold. And this intermediate 5D description has some particular, directions more natural in some sense. But when you glue things together,
In particular, if you put Neumann boundary conditions on the cylinder,
yes,
then you would once again get a continuous set of parameters associated
Right.
with holonomies.
right.
So that would become like the torus. Is this right?
Well, yes. Well, you need to worry if you can preserve the supersymmetry and so on.
Conceptually.
Conceptually, yes.
Do you agree with that? No, but Shiraz, the question is, I think, different. I mean, I'm just saying that indeed the difference between the torus and the cylinder should just be in the fact that there is boundary condition.
Right.
Yes.
But what I'm saying, there is an extra data, which is the holonomy, which is not. So the way
No, no.
I'm thinking is
No.
that as a 5D theory, this just give me just a second.
Yes.
Let me just say what I have in mind, then you can correct me.
Okay.
So what I have in mind is that when you put a particular holonomy, okay, which is the inequivalent ways of doing it depending on which dot in the Lincoln diagram color, gives you different 5D theory.
Right.
Right? It's various properties are different. The gauge symmetry is different, the flavor symmetry is different,
Right.
and so on, right? And now, I think what Shlomo is saying, you take that 5D theory and put it on a circle, which is like a torus thing
Yes,
from 6D,
Yeah.
should be the same 4D theories
that's right.
on the same conformal manifold.
That's right.
So here, for example, there is no puncture now, but this physical holonomy that is on the torus is still there, right?
It's there. Also, you can turn on this. You
But-
can turn
but
on
you
more
see,
than
you
one.
can go from one holonomy to another in the different
Yes.
U1
So let me
continuously.
say,
That's why we
exactly. So say you chose a holonomy when you went from 6 dimensions to 5 dimensions, got some 5D description. Then you can turn on some mass parameters in this theory. Okay, these mass parameters, you can think about them from the 6-dimensional point of view as other types of holonomies. And you don't lose this freedom in 5D. You have these parameters still there. Again, but the real thing that is, where you use the 5D description is how to put the boundary conditions. What do you mean by boundary conditions?
Yeah, the boundary conditions freeze you to particular values of the
Exactly,
right?
exactly.
Yeah, so had you just had free boundary conditions for the cylinder, then you could have said exactly the same thing for the cylinder, exactly what you said, right? Your holonomies would have been, you could vary them continuously.
Right.
yeah.
Okay. So we will have an example with different description, like in 5 minutes, and then I will later on discuss the conformal manifold a little bit in more
I'm
detail.
just confused with the fact that you can take the holonomy continuously from one U1 to another U1 and still get
Just think of it. You are say in the E string. In the E string, you took some holonomy and you went to SU2 with 8 flavors. You, for example, can turn on mass parameters for these flavors. And these mass parameters you can think of as holonomies from 6-dimensional point of view. Okay?
Sorry, if I had a particular holonomy,
Yes.
my 5D descriptions depend on the holonomy.
That's right. So there is some scaling. Okay, there is some scaling that you take. To get, you turn on holonomy and you choose some scaling, and then you get a particular gauge theory. But then you can take, mass parameters in 5D, and you can choose to scale them as you want. In particular, to go from one description to a very different one.
You're just making the strength of that holonomy 0.
Well, in some sense,
And
yes.
that
And
means
you might
you
go
get
through some strong coupling regime to go from one description to another. In 5D, you might pass through some strong coupling regime where you don't know what to do. So this is the qualitative picture.
And the different holonomies are all mass deformations of the same conformity.
That's right. You start from 6D. The only thing you can do is mass deformation, and you can scale them in like holonomies, which are
holonomies are masses.
yes, in 5D. Holonomies are masses in 5D.
It's a conformal manifold.
That's right, because it becomes dimensionless parameters when you multiply. Like you have a gauge field, and you multiply by the scale of your surface of the radii, and you can build dimensionless parameters from holonomies.
So there is a dimension. Why do I have masses then?
So
The holonomy should then characterize some my exact couplings, right?
yes, these are the couplings.
Yeah, etc. Yeah.
But why do you say masses?
So in 5D you can have masses. When you go to 4D, then the natural parameter would be the masses times the radius of compactification, and that will be your parameter in 4D. Your question is very good. I'm not claiming to have this distinction between masses and holonomies is a bit tricky. Again, as many things that I said, we understand them mostly by performing computations and then finding an interpretation to them. And filling these steps in the middle of the logic is not always clear cut. Could you guess it in advance? Could you say that you would get such and such exactly marginal deformations? It's not that there are questions. Why would you get? So I know, so for example, we have studied in another project, say, with Nati and Offer and Brian, compactification, say, from 3 to 2 dimensions. There, it's better situation because you have a Lagrangian in 3 dimensions, and you can do things. You can do exactly the same things. Turn on holonomies, and then you have a choice, for example, whether you scale the holonomy with the radius when you go to 2D or not scale. So if you scale, you get some parameters. You get some dimensionless couplings. If you don't scale, you get just some mass parameters, some real masses or whatever, so twisted masses. So here it's not so, because you start with a non-Lagrangian theory. I cannot tell, you start with a non-Lagrangian theory in 6 dimensions. This game is harder to play. We don't have that part, that systematic part of the story. This is the picture that you get. Okay, so this is.
Just one last question.
Yes.
Trying to understand this concern. You were worried about why the holonomies were connected. But is this more than just the fact that every group element can be connected with every other?
But then why is 5D description different?
Because you freeze the
but again, think of scaling. You think that you should scale things with a radius. Yes.
Masses can only connect with each other.
Right, and it's not connected through weak coupling. Like you need to go to large Young mills and then scale other things in some way. So things are connected. But it will relate to a puzzle that I will talk about a bit later. Okay. Okay. So this is one way dualities appear. Another way that I will not write explicit theories just because it will be complicated, but this simple equation, f1 plus f2 plus f3 equals f1 plus f3 plus f2, which is trivial. It translates, for example, to non-trivial statements, when you glue things together. When you have f1, f2, and f3, and you switch between 2 and 3, you will get different Lagrangian. But if this picture is correct, the theory should be equivalent in the IR. They should flow to exactly the same theory. And you can, we have studied many such examples, and always it is true because you can use some Seiberg dualities, some known Seiberg dualities to prove such statements. Okay? So from such very simple equalities follow Seiberg dualities. Again, if we did not know Seiberg dualities, you could think that they follow from this from consistency of this picture. Okay. So these are usual dualities that we encounter in these constructions.
And when you say you use Seiberg dualities and sometimes you mass up things, it's because on the moduli space there's no option but to mass up.
Well,
you cannot go to a point where you don't mass up.
Yes, this is another tricky question. I don't want to say that you don't have a choice. I want to say the other way around. There is a choice which makes it consistent. Okay. So
in his rules, he sometimes gets gauge groups and then masses up fields.
No, massing up actually is not massing up. I would say yes. There is no other choice because what happens is that, say you do Seiberg. First of all, you need to, here it's not complicated because it's only one gauge group. So there is one strong coupling scale and so on. So you go to low energy, and then you know that there is an effective description of the dynamics of this theory, which has mesons. And the charge of these mesons is exactly consistent with a mass term with this field. So by general rules of quantum field theory, anything which can be generated will be generated. So mass terms will be generated. And that's right. The full superpotential is very important. So it's not just some field. There is a superpotential, and the moment you have these superpotentials, mass term generically will be generated. So that's
a superpotential mass term would be.
Exactly. And then if you continue flowing to lower energies,
okay. Then you also sometimes go off on Higgs branch.
Exactly. That is trickier thing. That's what I was referring to. That you can make sense of it. And exactly arguing that it has to be, it's much more complicated. You need to, again, this usually happens when you have several gauge groups, and then you have to be careful, which dynamics you analyze first and so on. And that's trickier, but a claim is that there is a way to make sense of it. Okay, so let me now describe another type of duality, which is new, which is a bit surprising. So here we will generalize we will not discuss the E-string, we will generalize we will have more general reduction. We will start from dn plus 3, what sometimes people write as dn plus 3, minimal conformal matter. Minimal conformal matter in 6D. It's just a name, which again means one M5 brane on dn plus 3 singularity. Okay. So instead of having one M5 brane on D4 singularity, we'll have one M5 brane on dn plus 3 singularity. And here there is a claim that there are 3 different descriptions depending on holonomies that you choose. One of them is USP 2n plus 2n plus 6 flavors. This is 5D, yes. This is the 5D story. This is the 6D theory. And in 5D, when you go to 5D, there are 3 different descriptions that are known to humanity. So one of them is USP2n plus 2n plus 6 flavors. Another is SUN plus 1 plus 2n plus 6 flavors. Okay? And the third one, which is in a sense the direct generalization of what we had before, is the following quiver theory. It's 4, 2, 2, 2, 4, where there are n gauge groups here. Okay? These are effective descriptions in 5 dimensions. 3 different ones. Okay, the flavor symmetry is SO2n plus 12. Sorry, 4n plus 12. Yeah, good. Otherwise, it didn't work for me. So the symmetry is SO4n plus 12. This is the symmetry of the 6D theory. Okay, in particular, when n equals 1, it is SO16, which happens to enhance to E8. For other values of n, this is the symmetry. Okay, and you can see that here you have, like in these descriptions, you have manifest some bigger symmetry. Here, basically everything is broken to U1. You have 2 SO6s, but everything, and a bunch of U1. So that you need to turn on a lot of holonomies, the different holonomies, to arrive into such description. So the claim is that there is some choice of holonomy, which gives you these 3 very different descriptions. And you can see for n equals to 1, they are all the same. For n equals to 1, they give all the same descriptions that we have discussed before. So yeah, so this is, okay, this is a bit hard to see, but you should split the 2 into 2 and 2. And what you get is an affine Dinkin diagram.
Sorry, no, I meant the Dinkin diagram for SO2n plus 4n plus 12, and then coloring one dot.
Exactly. So, oh, you mean which holonomies to? I don't know that.
The commutant being precisely those.
Yes, I'm not sure there is a very clear-cut picture of that. I'm surely not aware of it. But what I wanted to say, that this type of description, if with a little bit imagination, it's just the affine Dinkin diagram of the corresponding group. And it's in general true. If you take AD type of conformal matter, the theory in 5D has, the quiver has such a shape.
Sorry, I'm not understanding. You're taking the 6-dimensional theory, putting it in a circle,
Yes.
and then is there a restriction on what SO whatever holonomies you're allowed to put?
Yes, so the claim is that with one choice of holonomy, with a very particular choice of holonomy, you will get this theory. With another choice, you will get this theory, and there is a third choice, which will give you this.
That surely doesn't exhaust all the
No, there are
other holonomies?
there are other holonomies.
And the claim is that those other holonomies are
We just don't. No. You can do whatever you want. The only question is, do you have a useful the 5D description or not?
Right.
So for 3 choices, such as the prescription is known, and here I'm just saying that this quiver has the shape of affine Dinkin diagram, and in general it is true. These are more exotic descriptions, which you can find with 1 and 5 brane on D-type singularity. For other compactifications, there is no simple generalization of these 2. Okay. So this is a very weird statement. Sometimes people refer to it as duality, as a 5D duality. This is very confusing, so let me just make a comment on that. So the statement is that you start from same theory in 6D. So there is some CFT, let me call it UV6D, which is this theory. Then you turn on different mass parameters, different relevant deformations. You put it on some geometry with some parameters. So these are some relevant deformations. And then you get this effective quantum field theories in IR. There is 1, 2, 3.
Sorry.
Yes.
Those flavors, they don't naturally seem to have the same symmetry.
Yes, they don't have the same symmetry because the holonomies broken those symmetries.
No, I'm saying in the effective description you've got some like 2n plus 6 flavors.
Yes.
That USP2n is not the rotation. Is not some rotational symmetry of these flavors.
No, it's some. Yes, it's a fundamental of the USP2.
Including the plus 6.
Yes, including the plus 6.
Ah.
So
Yeah, at least the rank of the symmetry should work. The groups shouldn't work because groups are broken by by the holonomies.
Wait, so for SU n plus 1, the fundamental has dimension n plus 1. So that would give you 2n plus 2. And then the remaining 4 singlets or something like that?
No. It's like 2n plus 6. So 2n plus 6, the hypers
those
2n plus
many
6 times the n plus 1. And these are hypers, so there are twice as like that.
And there's no rotational symmetry between these various fundamentals?
Oh, no, there is some symmetry which you can rotate. So there is some big symmetry which is preserved here, some symmetry which is preserved here, and much smaller symmetry which is preserved here. Just because here you turn on more holonomies. To get to this theory, you turn on more holonomies.
It should be commutant of your choice.
Okay, so US 2n is the gauge group?
Exactly. This
Oh,
is the
I
gauge
understand.
group. Sorry, I did not say it. This is the gauge group in 5D. This is 5D gauge, this is 5D gauge. And here the 5D gauge is SU2 to the N. Okay? And then there are two SO6s, the SU4s, SO6s in end, and there are many SO2s, U1s in
I see, now I understand. So for instance, that 2n plus 6
Yes.
would be exactly turning on a spinor holonomy in SO.
Yes, I think so.
Because
Yes.
it's a general rule that if you turn on half, 1, 1,
That's
1,
right.
1, 1, 1, 1, SO
That's right.
2n breaks to UN.
Yes, I think you're right. Yeah. Okay, so then we have this thing, third theory. So sometimes people call this duality, okay? But it's important to remember that it is not a duality in the sense that we are used to, like 4-dimensional dualities, where we have several different UV descriptions which flow to the same IR. It's the same UV description which gives rise to different IR theories with different deformations. It's just the UV completion of all of these theories is the same. Like you need to switch off these deformation parameters and then you get the same theory. So in that sense, it's a 5D duality between all these theories. But again, it's not that they are the same, they are deformations of same theory. So this is something you would never call duality in 4D, but that's what you have in 5D.
Earlier things we had to continue.
Sorry? Which earlier thing?
2 UV theories flowing to the same thing, even that was actually universal.
Yes. This is just IR equivalence. Yes. Okay. So this is one thing. So now we need to understand, now what I will do, I will produce same theories using these different descriptions. So one thing to do is to understand domain walls. Okay, so there are many, let me call this description 1, description 2, description 3. So it turns out that you can build domain walls between description 3 and description 3. This is very similar to what we had before. Okay, so we have some this type of gauge theory on one side of the domain wall, the same gauge theory on the other side, but the orientation of the holonomies is somewhat different. And that let me draw the domain wall theory that you get. It's very similar to what we had before. It will be something like that. Again, sorry, these are flavors. Everything is flavors. This is the Wezumino model. So something like that. Okay, something which is now looks much more complicated, but it is a straightforward generalization of the picture we had before. Okay. Again, there are n groups here. So if you take n equals to 1, this will be exactly what we had before. So there is some monstrosity like that. Okay, and there are these flip fields which are very important. So this is one domain wall that you can build. Another domain wall that you can build, this so happens, is a domain wall between 2, 1, and 2. So this is something which you can build. It's a domain wall which interpolates between this gauge theory and this gauge theory. And the theory is, again, a Wezumino model. So you have n plus 1 on one side. This is SUN plus 1. Then you have a 2n, which is US. You should think of it as USP2n. And then there are filled in 2n plus, there are 2n plus 6 lines. Okay.
This description was in the bulk, right?
Yes.
Now you have that. There are also going to be, when you pull these things together, you also need to tell us about holonomy.
Yeah. So what I'm telling you is what happens if you take the domain wall theory and already reduce it to 4 dimensions. So. So you will have some bulk fields, which are, for example, here are these 2n plus 6 that you see here and here. So we already added everything together and went to 4D.
Yeah.
Okay, so no, we did not cross. We are on a.
Coupling with the bulk, right? Is that global symmetry is precisely the gauge symmetry. So that's why there is a natural coupling to the bulk.
That's right. So this is an SUN plus 1. So you should think of this theory. You have some tube, the domain wall. Here you have an SUN plus 1 gauge theory. Here USP to N. So these are the degrees of freedom on the domain wall. Like this is the bifundamental of SUN plus 1 and USP to N. And there are these fields which are in the bulk, these hypermultiplets. For consistency, you need this. Actually, this is a field in antisymmetric representation of this SUN plus 1 that you need to add on this side for anomalies and so on to work. And then we just go to 4 dimensions, so no gauge fields. We just need to add these fields which have Neumann boundary conditions, and that's it. So I'm jumping to that already. Okay. So the point is that.
I mean, here in that wall, it's difficult to go to 4 dimensions.
Sorry.
Because I mean, in this 1 to 2 wall,
Yes.
there is difficult to go to compactify now, right? Because it's 2 different theories on both sides. How do
No,
you do
that's fine. I don't glue. I just reduce the tube.
Okay.
Okay, very good point. So now we have 3 types of different punctures. We have one type of puncture which is associated to SU2 to the N symmetry. This is the gauge symmetry of the 5-dimensional picture. This is this. We have one puncture which has SU N plus 1 symmetry, and another puncture which has USP to N symmetry. So very different looking punctures. We will be allowed only to glue same types of punctures together. Okay, but if we have a domain wall, we can glue USP to USP, and then there will be SU on 2 sides. We will be able to glue the SUs together.
But from the point of view of this compact, let's say before turning on this flux, I make
Yes.
porous, and
Yes.
then I turn on flux. Now what is
No,
the
no, no,
inherent
you cannot do
obstruction
that.
in turning on that flux?
Okay, so again, there is an order of limits here. To discuss these domain walls, you first need to turn on a flux. Otherwise, there is no point of discussing them.
I'm just saying from this picture,
Yes.
it seems that you cannot glue, right?
You cannot glue. You only without this picture you cannot glue. So what you can glue is to take two such things, and glue USP to USP, and then glue SU to SU. That you can do. Other things are not well defined.
But the flux is a quantized, maybe it's automatic. Then.
Okay. But now you see, we have these different descriptions, and I did not tell you what exactly the flux is not very important, but the flux is different of the 2 descriptions. But now it should be possible to engineer the same value of the flux using this tube, concatenating these tubes and concatenating these tubes together, okay, in some ways to produce equivalent theories, but they will look very differently. Okay, so let me now draw these things. And let me draw it here. Okay. These are the simplest things I can draw, which are not of the type of things that I have drawn last time, and they're already a little bit messy. So this is one thing you can do. You concatenate N plus 1 such tubes. You glue them together, and the theory you obtain is 4. And then you have like N plus 1 things here. Okay. I will not draw all the lines, but like there are 4s here and 2s here. And you can fill in the lines. These are just N plus 1 copies of this thing. So you just glue this thing together, and you glue it. You should think of it as glued on cylinder. So when you glue 2 such theories together, you attach one above. Yes, so this is a torus. And this is a torus with 1 unit of flux, which preserves a symmetry which is SUN plus 1 times SO 2N plus 10 times U1. So if you write the Dynkin diagram of SO for n plus 12, there is one node that you can choose that will break to such a symmetry. Okay? So this is the symmetry of this theory. Okay? You don't see it. You see only SO6 times SO6, and then there are a lot of U1s. Okay, just to tell you how you can see the SUN plus 1. So there are n plus 1 lines here. So they will form a fundamental of SUN plus 1. It's not, they don't form it in this description. But if you assign to them, for example, fugacity, say 1, 2, and so on.
The Lagrangian is manifest.
No, it's not manifest because they are charged under different gauge groups. It's not manifest. There is a Zn symmetry, but not SUN. Sorry, Zn plus 1, but not SUN plus 1. Okay, it's not the only manifest symmetries, non-abelian symmetries are these two SU4s.
So if you add these SUNs on the gauge field also.
Wow, it's not. You don't call it usually a symmetry of the theory. You want to permute. There is some discrete symmetry which also permutes the gauge groups. That I agree, but it's not a global symmetry. Okay. In general, you would not expect such thing to enhance to some non-abelian flavor symmetry.
Because the gauge field cannot be charged.
Yeah. Okay. So this is how this what becomes an SUN plus 1. The SO 2n plus 10 are these two SO6s and bunches of S.
Because gauge transformation rule is non-linear.
Yes, exactly.
Yeah, so
These are different.
Yeah.
Right. So, and you have a lot of SO2s here, like every, if you wish, cell in this theory has its own SO2, its own U1, so there are a lot of U1s, and they form this this bigger symmetry, and then there is one additional U1, for example, under which all these fields are charged in the same way. This is the U1 for which you turn on a flux. So there is such a theory. It's very, it's a big theory, a lot of SU2 groups, order n squared SU2 groups. But it's not very complicated. It has some structure. Now, the theory which is dual to it, which
is there particular reason that you turn on? What is this n plus 1?
So I took n plus 1 such blocks, okay, together, and the reason I take n plus 1 is that the flux
Is 1 over this thing?
is 1 over n plus 1
Why?
in some notations. That's what it is. Okay.
But why would one, I mean, if I didn't know anything, why would I consider such a unit of flux?
Oh, okay. So we can. This is this center flux that I mentioned. The moment you have punctures, you can turn on center, the flux in the center of your symmetry, and you actually can. This actually can. Again, that's not how we did it. We first understood the theories and then derived, but in retrospect, you can actually understand why it is.
Okay, but if I don't do n plus 1, I'm still.
You can do it. You can do it. You will break some of the symmetries. Like you will break the rank of the symmetries to some subgroup. These are okay theories, and you can also understand.
No, but then the fact the flux is not quantized should manifest.
No. So what happens is that any symmetry for which the flux is not quantized properly will be broken. You can just see it. Like
Is broken?
Sorry.
This U1 will be broken.
For example, well. It's more complicated than that. Okay. Basically, what happens here is that okay. You're asking excellent question. So the U1 that has a flux, well, these are not the same punctures. That's what happens here. Okay. So if you wish, the U1 is rotated in some way inside the big group, and when you add up n plus 1 such pieces, you get back to yourself and you don't break. But yes, the naive answer to your question is yes, you break that U1, but it's a little bit more subtle than that. Okay, so this is one theory. Another theory is just by taking this type of blocks and gluing them together. And the theory that you obtain has the following form. It's n plus 1 flavor symmetry. Then you have an SUN minus 1 gauge groups. Okay, so let me be a bit schematic, not write the arrows carefully. There are two antisymmetric fields here. And then there is a field which goes like that to n plus 5, like that.
This is the one with 2 walls.
This is the one which actually you glue. You see, there are 4 blocks So there are 4 walls like that that are glued together in a certain way.
SU, USB.
Exactly.
SU.
So there are SSU, USB, SU, USB. Okay?
Didn't understand. Sorry. This wall was SU to USB.
No,
Then
yes.
you put another wall which takes USB to SU.
So these are two walls. So this is the SU to the SU, and then you glue 2 such things together.
Yeah, okay.
Okay.
Yeah.
And it's not you need to split these things as we did with the E-string example for the flux to work. So this is the particular thing that you need to do. So the claim is that you produce the same value of flux. Okay, if you do the algebra, the same value of flux is produced, but here you see you have 2 SUN plus 1 gauge groups, 2 USP to N gauge groups, and very simple quiver, and this should be dual to this monstrosity.
Not just the same value of flux, I mean same direction. I mean,
Exactly same direction, same value. This is the same flux. Okay, the same symmetry should be preserved. Okay, so again, the details will take me 1 hour to spell out.
I'm
So
just thinking in terms of this Lincoln diagram point of view, where you denote the flux by U1
yes.
dot, right? But this I thought were 2 different dots.
No, but again, you can split. You can now start playing this game of some of the fluxes being positive, some of negative, and gluing things together, and eventually you get such a theory. They should be dual to each other. It's highly non-trivial, but they are. All the checks that you can perform, anomalies, indices, you can compute, and all agrees. Okay, and this type of duality, at the moment at least, we cannot reduce to non-Seiberg dualities. Okay, this follows from this 5D duality. Okay, because we had different 5D descriptions, and that's why we can engineer such a 4D duality, and it looks really like it doesn't reduce. You cannot deduce it from moves, Seiberg duality moves on single gauge group. Seiberg duality is something that you do on a single gauge node, and then you can do it in various ways, and that's how you show that quiver theories are dual to each other. Here, the number of gauge groups here is order n squared. Here, there are just 4 gauge groups, so it's not clear we don't have a proof that it doesn't reduce to Seiberg duality. There might be some clever way to do so, but at least at the moment, this looks like a new type of duality which works at the quiver level. Okay, it's not a move on a single gauge node. It's like this quiver is dual to this quiver. Okay, it will be nice to understand if you can prove it by Seiberg dualities.
The top theory has some these SN discrete symmetry.
Yes. So this is
Hands
not
into some continuous?
the symmetries. The manifest symmetry here and here are different, and the claim is that both of these theories have this symmetry in the IR. This Zn plus 1 is part of the center of SUN plus 1, if you wish. Here SUN plus 1 is manifest, for example. Okay, there is an SUN plus 1, it's manifest, but SO2n plus 10 is not manifest. And SUN plus 5 times U1 subgroup of it is manifest, and then when you look at the representations in the index, for example, they form the right representations, and these two agree.
More than Zn plus 1, right? Isn't it Sn plus 1? Just permutations?
No, because there are lines that I have not drawn. There is this structure. It's a rigid. It's a triangulation of a solid cylinder.
Yeah.
Yes, so you can just rotate. Okay, so this is one thing. And again, to Shiraz's question, to analyze the dynamics of this theory, for example, is rather tricky, because if you make the analysis, of beta functions and so on, this is not a conformal theory. And for example, you will find that the SUN plus 1 theory is IR free. If you just look on this node, it's IR free. The USP to N is asymptotically free. So you can say, okay, how do I make sense of it? So now you have several strong coupling scales. So what you can do is first analyze, switch off completely the coupling of the IR free theory. So don't gauge that symmetry. First analyze the USP to N dynamics. And then you will see that, after you do that, at the fixed point, this becomes actually conformal. Okay, so the beta function changes in the IR, and that's how you make sense of it. So there is a way, there is an RG flow there is a way, so it's like dangerously relevant coupling, gauge coupling. So there is a way to make sense of it. So it's not absolutely clear that with any choices of couplings you will end, but you can argue that there is a direction in the RG flow which will lead you to a CFT, and that CFT will be the same CFT as this CFT. Okay.
By the way, so
Yes.
it's not something that you're talking about. One thing that one could have done is this with the cylinder, right? Where let's just take the cylinder without flux, where you turn on the holonomy and you obtain some 5D theory,
Yes.
and there's some boundary conditions on this.
Yes.
Now, when you glue them, you could turn on transverse holonomy,
Yes, you can.
and then there will be some duality between A cycle and B cycle.
Again, if you don't turn on fluxes, these constructions are sick, so I cannot tell you what will happen. But yes, you can do that, and this will correspond to some like when you go to 4D, you will have couplings which will correspond to these holonomies and also to these holonomies. Okay. So I'm going much slower than I intended, so I will do some less things than I intended, but that's okay. So let me just.
Sorry, when you have flux through the torus, isn't it that both holonomies are reduced automatically? Because
Well, you mean with this argument that to get a gauge theory we had one holonomy and then, well,
just geometrically, when you have flux through the torus,
yes.
isn't it that
It's just you can have one holonomy, but its value depends on the other direction. That's how you can engineer the flux. That was the argument for the domain wall. Okay. So let me now mention several things. Okay. So one thing that I want to mention as an open question is that actually when you look on this type of theory, okay. So remember this.
Sorry,
Yes.
sorry. So the holonomy will be some group value, right? Holonomy is group value,
Yes.
right? So you have A holonomy and a B holonomy, and I think the flux is precisely the A, B.
No. There are holonomies and there are fluxes. There are different things. If you can have flux without holonomies and holonomies without flux. That's if you have space time like holonomy which depends on on some special direction, this can produce flux. But if you can have like constant holonomy around one cycle and constant holonomy around other cycle, this will not give you flux.
In that case, they would commute.
Yeah, that's right.
No,
That's right.
billion holonomies, may not commute, right?
No. But you like for consistency, you need the holonomies to commute. Like you can open the Riemann surface and go around all the cycles and.
No, what I'm saying is this case here, in the thing that you're doing, where
Yes.
you have holonomy and a flux.
Yes.
I'm seeing the holonomy, the transverse is automatically non-trivial, and it would be the non-commuting one, which would be related to the flux.
Okay. You might think about it that way. I don't think about
Well,
it.
because the reason I think about it is that now there is another type of thing that I can try to do, which is to exchange the cycles. And I could turn on the holonomy that was the flux, and the flux that was the holonomy in some sense. That's
Okay.
not what you're doing, but I just.
No. Actually,
I'm just
okay.
saying this.
We can discuss it, but there is something like that, which again looks almost well. Okay, we can discuss it.
Okay.
But there is something. Okay, so let me see how much I can do in half an hour. But let me mention.
Sorry, but just to say, suppose we just take a U1. You forget the non-linear. So you could turn on a flux. In addition, you could turn on flux.
Yes,
So these are not,
that's right.
yeah, they're two separate parameters. Number of units flux plus volume.
No, but in the non-abelian case, the flux and one cycle, holonomy along one cycle will tell you what the holonomy along the other cycle is.
And
Up to some conjugate.
again, if you turn on commuting holonomies, so for non-abelian group you have you have a flux in the say in the U1 subgroups of this non-abelian group, and you have commuting holonomies. These are two distinct things.
Yeah, I agree. Are you going to allow these SUN fluxes? That's what you're thinking of? Oh, later, let him finish.
Okay. So let me make a couple of observations. So one observation that I want to make, which is very interesting, and we don't have an explanation for it. So there is this quiver theory that we obtained by taking this dn plus 3 theory on a torus with some value of flux. Okay? We have analyzed other types of compactifications. For example, you can take 2 and 5 branes and say that the value of the flux is f. Okay? Then we can take 2 and 5 branes to probe z f n plus 1 singularity. Okay? Completely different. This is one 6D theory, this is another 6D theory, and compactify it on a sphere with some types of punctures. There are 2 maximal punctures and some number of other punctures. And the theory that you find here is almost identical to this theory. It's up to some free fields, it's the same theory. So, and there are a lot of identifications like that. So starting from different theories in 6 dimensions, doing different compactifications might land you on the same theory in 4 dimensions. Even it looks not a trivial theory, but there are such identifications, and we don't know at the moment how to explain this. So one compactification that you can consider is this type of CFT. You take 1 and 5 brane on dn plus 3 singularity, put it on a torus with flux. Okay, you get this type of theory. You can consider another 6D CFT, which is 2 and 5 branes probing ZF n plus 1 singularity, okay, where flux is in the type of the theory. So here you have a theory and you have a flux. Here the flux is in the type of theory, and you get, and there are some number of punctures. There is n plus 1 punctures here, 2 maximal punctures here, and you get the same type of quiver up to some free fields. So not a trivial structure, but the same structure. Why? We don't know. So there might be some string, M theory dualities which relate this geometry to this geometry. So there are a lot of things.
Opposite of what you've been doing so far.
Exactly. So, but it is an interesting question to which we don't have, and there are many such equivalences. Okay, so you can get the same complicated theories in 4D by doing very, very different geometric engineerings, and most of them, at the moment, there is no understanding why they are the same. They are not exactly the same. They're almost the same. Up to some free fields, they are the same. So it might be, these free fields are very important, for example, for matching anomalies. Okay, there are fields you need to have them to match the predictions that you have from 6 dimensions. But the CFT, the interacting part, looks the same. So the question is there a reason for that? Okay, so another thing, maybe the last thing I will do, I will not have time to discuss trinions, but you asked a lot of questions about this marginal deformation. So let me maybe discuss those. So there are 2 things I want to say about that. So one thing is that there is a general prescription to predict what will be the deformation, the marginal and the relevant deformations in 4D that I mentioned in the seminar, I think, and I want to talk a little bit more about it. So let me give you a formula, like what is the prediction. So say you have a 6D theory with symmetry, which is G6D. Okay? And let me talk in characters, because then it becomes simple. So say you have a character of a joint representation of this 6D theory. Then say for simplicity, we pick a U1 inside this 6-dimensional theory such that the commutant of this U1 is G prime inside this G6D. And we turn on flux in this U1. Okay, I again will pick only one U1. The generalization is rather obvious. So one thing that we can do, we can decompose the joint representation of G6D into representations of G prime and U1, charges under U1 and representations. Okay, so there will be some sum, and this A will be, say, the fugacity for this U1, and there will be charges Qi, and there will be some representations of this G prime. Okay, some decomposition like that. Okay, so this is just group theory. Then the statement is like that, that the number, or say the representation of the relevant operators of the 4D theory that you compactify on genus G-Riemann surface in presence of flux F in this U1 takes the following form. You sum over i's such that Qi are smaller than 0 in this decomposition. And you have characters of Ri G prime times a to the Qi G minus 1 minus Qi, this flux F, and I assume that flux F is greater than 0. Okay? And the number of marginal operators is 3G minus 3. Okay, these are the complex structure moduli, plus the things which come from the holonomies. So in this language, it will be I Qi equals to 0. Chi Ri, G prime, G minus 1, and that's it. And actually plus the number of U1s. Well, it's a more tricky thing to understand, okay? So there is a very concrete formula which predicts the number of relevant deformations and number of marginal deformations. And the way to understand these formulas is to start from 6 dimensions, to think what are the generic operators that you have there. There is a stress tensor and there is a conserved current. And then you think, you know, just do basically Riemann rock. You integrate over Riemann surface. You take, for example, your conserved current or some descendant of that conserved current and integrate it over some function on this surface. And ask yourself, what type of operators of this kind become protected operators in 4 dimensions? So it's some cohomological problem. You need to solve, you know, which operators of this type are BPS operators in 4 dimensions. And this is just, as you can see from, you know, from the answer, it is just some cohomological answer. Okay? So there is a very well-defined prescription to what are the relevant operators and what are the marginal operators. And this part can be thought just as a dimension of the space of moduli space of flat connections, of holonomies on the Riemann surface. So all the cycles, you turn on holonomies around all the cycles, and that's what you will get. Okay? And if you are computing compactifications with general genus, this turns out to be the correct answer, like in many, many examples. Okay? Except for the torus. Okay, so, and let me discuss the torus a little bit. Do you have questions about this?
So this includes both the holonomies and the fluxes?
No, fluxes don't contribute. So flux determines how many different flux gives you different theories. So different fluxes will give you different theories, and those theories will have different numbers of relevant and marginal deformations.
Because you can turn on only those holonomies that commute with fluxes.
Exactly, but also like the number of deformation, like the bigger the flux, the more deformations you can turn, is basically the analysis of this thing. Like what type of operators, like you take this, your BPS operator on 6D, you smear it on the Riemann surface, and then how many BPS operators you get in 4D is actually affected by the value of flux.
It's something like monopole spherical harmonics, that the number of 0 modes in a monopole background depends on the flux.
I think you can think about it in that way.
But why relevant and marginal like that?
Sorry?
Why relevant?
So-
Marginal.
So it's just different cohomologies. Basically, when you, so there is a relevant. So you see there is Qi smaller than 0. This is Qi equals to 0. The Qi bigger than 0 become irrelevant. But irrelevant, you know, there are a lot of irrelevant operators. Okay? So some of the irrelevant operators will be of the, you can write a similar formula for them, but there are a lot of them.
Relevant operators, marginal operators from not conserved currents, but some other BPS operators.
Very good point. So generically, you know, you have some spectrum of operators in 6D with some charges, right? And in some sense, the lowest operators are these conserved currents and the stress energy tensors. There might be others. And the others can give rise to additional operators. Typically, they don't. Okay? But in principle, that's the computer. You need to write the full spectrum and do this analysis for all the operators. But these are the operators which will be there. You can ask whether these are the only ones. And typically, they are the only ones for large enough value of flux and for large enough genus. These are the only ones.
So this analysis one can do for any BPS operator. Then?
Yes.
So that means the index should give you the index of 40.
Well, yes, but you need also to understand surface operators in 6D, because surface operators can wrap the surface and give rise to local operators. Okay? So let me now give you a puzzle.
And those don't give you light operators.
No, they can. Typically they don't, but they can. So let me give you a puzzle, and the possible resolution of that puzzle is exactly that something like that happens. And the puzzle is very well known, and it is funny that appears in this context. So let me go back to a string. So remember that we had this theory, which corresponded to compactification on a tube with some value of flux, which was half integer, and we constructed from this a lot. Yes.
Just clarify. The reason the answer depends on flux is that the rules for when something is supersymmetric depends on when the flux is, what the flux is.
Basically, yes. Right. So you see, the number of marginal deformations.
Very different in 4 dimensions. But 6 dimensions, you're doing the analysis in 6 dimensions, right?
That's right.
So in the 6 dimensions, how does it enter?
Okay. So this is Riemann.
Yes, exactly. It's just, if you wish, it's just Riemann-Roch. That's what it is. Okay. So there is this theory which corresponds to a tube, and we used it to construct many different theories. One thing which we did not do is just take this tube and close it onto itself. Okay? So let's do that. And what you obtain is this simple theory, which you all know, and whether you love it or not, I don't know. So this is almost SU. So it is SU2 with 8 chiral fields, but there is a superpotential. So actually, the SU8 symmetry will be broken to SO8. Okay, this is just SU2 with an adjoint and extra singlet field. But so it's almost n equal to SU2 with 4 flavors. Okay, so this is the if you wish, this is another example of a compactification that, like this theory up to this gauge singlet fields, you can get from other, like you take a 2,0 theory, you compactify it on some Riemann surface, and you get this theory. So this is another example of this phenomenon. But there is this theory, and it was observed a long time ago. Well, this theory has obviously an SO8 symmetry. You can see it with your bare eyes here. But it also has, if you compute its index, you see that all the states of this theory form F4 representations. Okay? Something which is very funny. This theory definitely doesn't have an F4. You can check it, and it doesn't have an F4. If you assume that it has an F4, you very quickly find some inconsistencies. Basically, this theory has a one-dimensional conformal manifold such that SO8 is preserved on each point of this conformal manifold, and that's it.
Why cannot 4 emerges from the other point?
No, you can okay. So yes, there is an argument why you cannot do it. So, so for example, there is a neat way to understand it from the index. You don't need the index, but there is a neat way to understand it. Okay, let me tell you the physics. It's actually simple. So if the symmetry somewhere enhances to F4, you need to have a conserved current of F4. Okay, if you have a conserved current of F4, you know this number, marginal operators minus a conserved current, is an invariant. Okay, so you need to have more marginal operators which appear at that point. But then, by knowing marginal operators, there is a procedure to count exactly marginal operators. And you can see that you just cannot, you will get the wrong number of exactly marginal operators. Like this theory is weakly coupled. It passes through zero coupling, so you know what is the dimension of the conformal manifold. And the dimension of conformal manifold doesn't change. Okay? And assuming that there is an F4, okay, you will arrive at some nonsense. So that the dimension changes or something like that happens. Okay. Yes, something weird happens that cannot happen. Okay. So now let us think, it was a puzzle. Why you see here F4? Okay? But from this perspective of compactification, you actually expect F4. So what is the expectation from the compactification? Expectation from the compactification, if you can analyze these types of formulas, and expectation is that you have actually more than one-dimensional conformal manifold. It doesn't matter how much, you have more than one-dimensional conformal manifold. On general point of this conformal manifold, the expectation would be that the symmetry is broken actually to U1 to the 4. Okay? And that there are submanifolds where the symmetry enhances to SO8. There is another submanifold where the symmetry enhances to F4. And actually there is another submanifold where it enhances to USP8. So there is a very rich structure that you would expect from these naive arguments. Okay? But when you actually do this is a very particular theory. You study it, you only see this, this conformal manifold. The other parts are not reached. Okay?
If you break SO8,
You cannot break SO8 on the conformal 8. The SO8 is preserved on the conformal manifold. You cannot break it. Okay, this theory has only n equal. Moreover, supersymmetry is not broken. Like you have n equal to supersymmetry on all of the conformal manifold. So this is a puzzle, but the possible resolution of the puzzle is exactly these things. That naively we expect a lot of like a big conformal manifold with very interesting structure. But something in this logic goes wrong. There are a lot of things that can go wrong. For example, it might be that these marginal operators, they cancel out against some accidental conserved currents when you do this reduction, which come from some other operators in 6D. Maybe surface operators, maybe other operators. We don't know which. And somehow you cannot access other points in this conformal manifold. You can only access these points. But group theory is so strong that it tells you that, whatever it is, even if you can only access this part of the conformal manifold, everything should be consistent within principle having these points on conformal manifold. So everything is actually in you can interpret it as representations of F4 or USP8, although there is no F4. So there is this, conceptually there is this similar, the people were discussing this moonshine phenomenon where you see some symmetries in partition functions which are not symmetries of the theory. So this rings a very similar bell. Like there are representations that you can see, but they are not representations of a symmetry of the system. It's somehow you just cut, like something carves out part of the parameters of the system, and you don't see all of it.
You're saying you can group the index into representations of F4?
Yes.
Even though you don't see the F4 couplets?
Right, exactly. But yes, and you see, F4 is a bigger group than SO8. And F4 has an SO8 as a subgroup, but the SO8 you see is not a subgroup of F4. For example, the 28, the joint. You see in some places the 28 of SO8, but in terms of F4, it's 26 plus 2 singlets. It's the fundamental plus 2 singlets. But the characters work out correctly. You see the characters. You see only the representations, which are consistent, with reinterpretations of them as F4 or in fact as USP8.
USP8 and F4, they are not a subgroup. Neither one is subgroup.
No, I don't think they.
Or the other, right?
Yes.
So shouldn't the group be larger?
No. I don't think so. Because you can have, it's not that any representation can appear. This is some restriction on representations which appear.
But the index is while group invariant under the while group of F4 and also invariant under the while group of USP8.
Yes.
So, and none of them is a subgroup of the other. So that means.
But also this SO8 is not this subgroup of F4.
It is.
No, this SO8 that you see in the index is not.
Not, yeah.
So the while group of this SO8 is not a subgroup of while group of this
so
F4.
shouldn't the symmetry be much larger?
So this is related to duality, like the relation between these two was understood as duality, like there is a duality group acting on the conformal manifold of this theory, and say the index is independent of couplings. So it's you see this discrete transformation, duality transformation as extra transformations. The USP8 part was not analyzed, I think. Maybe it was analyzed in the math literature. This appeared in the math literature, the fact that it has an F4. So this is an interesting puzzle that one needs to understand. I wanted to discuss also three puncture spheres, but it will take me 45 minutes, I think. So I think, let me see. Yeah, I think I should stop.
But maybe you could just tell us, so the theory of a generic three-puncture sphere
Okay.
is known?
No, okay, so let me try to summarize it quickly. So, okay. Okay, so what we have analyzed, and rather systematically, modulo the fact that one needs to understand these domain walls, and there is no systematics in understanding these domain walls, but there is a problem to solve. Understand domain walls, you will understand the tubes. Now, what is the situation with the three punctured spheres? With the three punctured spheres, the situation at the moment is that there is no procedure at all, which is systematic to understand them. What we can do is we can take the 6D theory and take its anomaly polynomial and analyze, integrate it over such a surface and predict what are the anomalies of such theories. Okay? We can predict the anomalies of such theories. We can predict the deformations according to formulas of the type that I just have written down. Okay? You can predict certain properties. For example, in class S, which has n equal 2 supersymmetry, people also were able to compute the Seiberg-Witten curves. Okay. And some other properties. For example, there are certain types of correspondences, like AGT correspondence, so you can understand how this type of objects fit into some types of relations between two-dimensional, four-dimensional physics, and so on. But typically, we don't have a Lagrangian for such theories. We don't have this picture that you have a 6D and a CFT in 6D, UV CFT in 6D, that you flow to 4D, some CFT in 4D, which is IR. That using such arguments, you can predict a lot of properties of this CFT. Okay? But typically, we don't have a CFT in UV, which is weakly coupled in 4D, which will flow to the same theory. There are some exceptions. Okay?
But let's take the cases where the holonomies of the three punctures are holonomies where you know the 5D description.
No. So this we discussed with Abhijit a little bit. So what you would need to know is, so you can divide it into tubes, and then the question is how you glue these tubes together. Okay? Even setting us up this question was not done. Like what exactly you need to have. So you have these tubes, and how do you glue them together? What do you need to do? What does it mean? Yes.
So in 5 dimensions.
Exactly.
Some boundary condition on 3 copies of 5D theory.
Right.
Right, folding click and so on. But what is that boundary condition? I think the only principle that would allow you to determine it is the crossing symmetry. That you glue it this way and you glue it that way, it should be the same. What is the other physical principle which will tell you what to do?
So, yes. So at the moment, there is no, this is completely open question. So the things that we know are kind of accident. So one thing.
In Eric's 2-story, it was useful to consider minimal bunches.
Yes.
Maximum
I would have discussed it in 45 minutes, but I don't want to. So for example, this is a three-punctured sphere. It's just a trifundamental of 2SU2. So if you take A1 type of 2,0 theory, 2 and 5 branes, and no singularity, just compactify them, by just, if you wish, by matching anomalies and Seiberg-Witten curves and so on. This is an n equal 2 theory. This is the three-punctured sphere. Okay. Another theory we discussed in the seminar, we had a 4-punctured sphere, which was an SU3 type of, like we have trifundamentals, but it's a gauge theory now. So this is a 4-punctured sphere, if you remember. And this, here we turn on some baryonic superpotential. So again, this is a Lagrangian, this is a building block which can be used, but as we saw in the seminar, this was just a guess, okay? There is no systematics here. As Abhijit was telling, in some cases, what one can do is the following thing. One can actually find some three-punctured spheres, again, just by, basically by guesswork. But where two of the punctures are these maximal punctures, that means that their symmetry is the symmetry of the 5D description. And the third puncture is some kind of smaller puncture. It's some puncture with much more restrictive boundary conditions. Okay? But then there can be some duality. Say you compactify on a sphere with 4 punctures, say, such that you can decompose into 2 3-punctured spheres, okay, using these Lagrangian descriptions that you have for these special trinions. Okay. And then there should be, if this dictionary is correct, there should be another duality frame where you glue this kind of 3-punctured sphere with 3 maximal punctures that you don't know about, and with another 3-punctured sphere with 2 minimal punctures, 2 other types of punctures and these maximal punctures. And in some cases, you can exploit such dualities to understand what this 3-puncture is. Just basically, you know, this is a Lagrangian. This you can show is a Lagrangian. And then, you know, you have a Lagrangian theory, which is equal to something that you don't know. You gauge some symmetry of it. You add to it some stuff. And these two should be dual to each other. Now, because you add some stuff to it, you don't just gauge the symmetry. You don't lose all the information about this theory. And in some cases, you can really physically exploit this duality by gauging some symmetry, using some supersymmetric dynamics to actually ungauge this procedure and derive at a description of such a theory. But it is very indirect. We can do it in very limited cases. For example, for E string, this can be done. For E string, we have a trinion which was obtained in such a way. Okay? So for E string, we have all possible Riemann surfaces, but the 3-puncture spheres are very complicated theories. I mean, we can use the description to compute anomalies, indices, any type of partition function that you want, which doesn't depend on the couplings, can be computed with those types of descriptions. It's exactly like the Lagrangian we had for the E6. It's you need.
But at the end, is there some simple Lagrangian for this?
No, so the Lagrangians that you have are of the type that you have a Lagrangian, you need to tune the coupling to some cusp where some symmetry enhances, some U1 enhances to SU2, then you couple that SU2 to dynamical gauge fields, and that is your Lagrangian. So it's not a good Lagrangian to compute correlation functions because you need to go to some strong coupling. But to compute indices and anomalies and so on, this is perfectly good. So this is type of Lagrangian we have for a string, a 3-puncture sphere. Okay, so this is the situation now. So it's a big, I think it's a solvable, but it's an open problem.
Do you need to turn on fluxes after the operation?
You don't have to, but turning on fluxes might simplify the problem. For example, typically when we know the Lagrangians, even this Lagrangian is a Lagrangian with a flux, with the flux which preserves an equal to supersymmetry. So typically the simplest Lagrangians that we have for the 3-puncture spheres have some flux, some non-zero flux. But in principle, there is no principle which tells you have to or don't have to.
Because you could put all the fluxes on.
Exactly. Like the moment you have these flux tubes, you can compute Lagrangian with a flux and then kill the fluxes just by gluing this.
So I suppose I was wondering, there's no special flux that you can only get when you have the fluxes are just sums of three.
Well, here there is this subtle question of these fractional fluxes that appear here and there. So sometimes, so again, there are some fluxes which are allowed when you have such a thing, which have certain quantization. And sometimes we get very weird types of fluxes that are allowed on 3-puncture spheres that you cannot engineer in such a way, and we don't understand it fully why these fluxes, for example, are allowed. When we're saying we get these fluxes, what it means, we get some theory which if you anomalies of which match with six-dimensional theory if you plug in some weird flux. But if you build from these theories things which comprise, allowed fluxes, you always get the right things. So it's not clear. But maybe it's a fluke, of the construction, or it's something physical. It's not clear. So, but in principle, I would say you should be able to put flux zero, like naive, say integer fluxes. You should be able to put flux zero here, and then just glue to it these flux tubes. Weird fluxes need to be understood. That's right.
There has to be these holonomies need to add up to 0, right? H1 and H2 need to be H3. So you would need only these 5D.
Oh, you mean that these types of punctures are correlated, as we discussed?
Yeah.
Yes, that is true. Okay, so again, there is this extra layer of subtlety that, even when we know the three punctured spheres, we know it for only very particular types of punctures.
So you can glue this tube with a flux
Yes,
on one leg. It should be the same as gluing it on the other leg.
that's right. That's another type of duality. Yeah.
No, so that could be a principle to fix this.
Well, it might. Yeah. Okay. I'm viewing it as a consistency check, but yeah, if you can use it as a.
Is it clear that it should be same as gluing on? I mean, suppose now we glue this and that to something else. Then on this cycle there would be a flux.
Yeah. So I think if the picture is in all cases we know this is true. That doesn't matter where you put the flux. So for example, you are saying you can.
Flux is like a point. You can tune it, turn it through a point, right? The point can be moved to any end.
Like as we discussed before, it seems that the flux can be moved from one place on the Riemann surface to another without changing the 4D theory. Like the compactification is independent of the of exact form of the gauge field you turn on. It only depends on the value of flux.
Oh, right.
But I was just wondering, you have to get on all 2 cycles. You measure the flux.
Yeah.
That has to be the same. Then once that is met, then you
Yes.
can move the flux anywhere you.
That's
anywhere
right.
you want.
Sorry, I
Yes.
misunderstood one.
So you've got, let's say you take this 3-punctured sphere
Yes.
and you build some complicated Riemann surface
Yes.
by gluing them together.
Yes.
Then now you put fluxes on particular tubes.
Yes.
That will give you some fluxes for some of the 2 cycles of the complicated Riemann surface.
2 cycles.
What do you mean? But there is only one
Oh, there's
cycle.
only one, two
Yes.
cycles. Sorry. Yes. Okay.
So yeah, so that like any way you spread the fluxes should be the same. And again, this is another very strong consistency check
Yeah,
on
I
the
think,
pictures.
Yeah, already in this, just in this three-punctured sphere, okay, the three-punctured sphere is like a particular boundary condition of some 5D theory, 5D theory, 5D theory, right?
Yeah.
And now you couple this 5D theory to a domain wall
Yes.
to the flux theory, and that should be the same as coupling another theory there to a
Yes.
different 5D.
But it will be another theory because the puncture is different.
Yeah, it's a different thing. Yeah.
And you need and the tube will, you need to do it in a consistent way, but there should be a way which is consistent.
So this is like yourself, the way you do this.
Sorry?
Use the index, for example, by difference operators.
Yes.
This is a difference. You can think of this gluing as an operator.
Yes.
And
As an
sign
integral
It's
operator.
a kernel.
Yes.
We're talking about.
Yeah, yeah.
It's an integral operator, and it shouldn't matter where it hits.
That's right. So yes, maybe if somebody is smart enough, these consistency conditions can be integrated in some way to determine, maybe the index of these theories, or maybe a Lagrangian for them. So what I'm most interested in is in finding this for the Lagrangians, like not just the index or the anomalies, but is there a description? A description?
Computable.
Yes, exactly.
But
In
why
principle.
do you think it should be? Maybe for the TN
So
theory,
this was
or
question number 1. When in the first lecture I listed questions, that was question number 1. So I think it's a very interesting question, whether any conceivable CFT can be reached by an RG flow.
For example, TN theory is probably the simplest theory to look at in this context.
Well, maybe. So as you know, we can do the A6. We can have a
But that's
Lagrangian.
strong coupling.
Yes. So maybe one can do better. But for Argyres-Douglas theories, for example, at the moment we have
Yeah.
completely well-defined usual Lagrangians This is work by Mariusz and Son, which is beautiful. You know, 20 years ago, nobody would believe that such Lagrangians exist, but they exist, so why not? Okay, so this is the program.